Okay, in section 2.2 we're going to talk about limits and actual definitions of limits instead of sort of what we did in the last section where we kind of talked about this is what it's approaching, that type of thing. I'm going to talk about that a little bit more, but we're going to be more specific about it. So let's draw a couple pictures, and we're going to talk about limits in three different ways. One sort of graphically, one numerically, and then one algebraically. But we're going to start with the graphical version first. So let's say we have a graph, and maybe this graph, it's piecewise. We have a hole in it here. We've got this point, and we've got it to continue on here. Now, a limit, let's say I'm approaching x equals a right here. Okay, so there's this point on the graph right here at a comma f of a, and that's what we're going to start looking at. But as these x values, if I take points on the x-axis and I get closer and closer to a with these points, right, then they correspond to points on the graph that get closer and closer to this point at a comma f of a. Alright, so we've got some notation for this that I'm going to write down. And what this notation looks like, it's got this limit. So it's the limit, and it says the x values get close to the value at a. And then over here, after the limit stuff, we put in f of x. Okay. So what this says is the limit of f of x as x approaches a. That's how you would read that expression right there. Okay. In this case with this graph, I'm looking at x values that get closer and closer to a. So I'm getting closer and closer to a on the x-axis. And we want to know what the y values do as I get closer and closer to a here. So I'm taking points on the curve, and I'm getting their x values to get closer and closer to a. And we want to see what their y values are doing. Well, at this point, those y values are getting closer and closer to f of a because this is a continuous function. So if f is continuous, this limit as x goes to a of f of x equals f at a. Okay, let's look at this other point on the graph here. Let's look at this point at b. Okay, if these points get closer and closer to b, I want to know what the outputs of the graph are looking like. So here the output, let's maybe say this is at 1, and let's say this is up here at 2. As these values get closer and closer to a in the x direction, right, the y values are getting closer and closer to something close to 1, right? But if I'm coming in from above, in the sense that the x values are getting closer to b from above, right? We were looking at from below before, now we're looking at from above. From above, these y values are getting something to be something like 2. Okay, so I can't just say as I approach b, the outputs approach one number. If I come in from the left, they approach 1. If I come in from the right, they approach 2. So at b, this limit does not exist. So the limit of f of x as x approaches b, it does not exist. Okay. So there's a couple reasons why we might have a limit that doesn't exist, and this picture shows us what's called a jump discontinuity. Let's look at another reason that the limit might not exist. Let's look at the graph here. Let's look at f of x equals 1 over, let's say, x squared plus 1. Okay. Sorry, not x squared plus 1, just x squared. So the graph of this looks like this. We've got this vertical asymptote at 0, and we've got horizontal asymptote at 0 as well, but both sides kind of go up. And I'm going to make this a piecewise function so that I can define this everywhere. It's going to be 0 if x equals 0, and it's going to be this if x does not equal 0. So the full graph of this is going to be all of this curve and all of this curve and this point at 0, 0. Okay. Let's see what happens as we approach 0 on the x-axis. So we want the x values to get close to 0, and we want to know what f of x does as these x values get close to 0. So I'm going to be moving in towards 0 from the left and from the right. And as I move in from the right here, these y values, these outputs of the function, keep getting bigger and bigger and bigger, right? They go off towards infinity. As I come in from the left, these y values also get bigger and bigger and bigger. They go up towards infinity, right? This point at 0, 0 has no bearing on what's happening to the outputs as we get close to 0, right? The limit doesn't take into consideration what happens at the point itself, just at what happens to the values near that point. So these values are getting close to infinity, these values are getting close to infinity as the x values get close to 0. I will say that this limit is equal to positive infinity, but that's also not actually a number, right? Infinity is not a number. So this statement here does not say that the limit exists. It says it diverges to infinity. This limit doesn't exist. The limit diverges to infinity. Right. To converge means things are coming together. Diverge means things are spreading apart. Well, the outputs are getting further and further from real numbers. They're going off towards infinity. They're diverging to infinity. Okay. Remember, this point here had no bearing on whether the limit existed or not. Right. Let's see another one. Let's look at f of x equals 1 over x. So it's going to be a similar graph, except for the left side goes down, the right side goes down. Okay, so and we'll put a point at 0, 0 again. So we'll make this piecewise 0 if x equals 0, this if x is not equal to 0. Okay, so we've got that whole graph there. Again, it doesn't matter what that point in the middle does, because the limit as x gets close to 0 of f of x, the point itself at 0 has no bearing on whether this limit exists or not. We're wanting to know what happens to the values around this point. So as these x values get close to 0, if I'm coming in from the right, if I'm coming in from the right, these values, these y values, they get bigger and bigger and bigger. The function values get large. If I come in from the left, and I get close to 0 with the x values, the y values get really, really big negative. This doesn't exist, but it doesn't equal infinity or negative infinity. They go in different directions. It still diverges. This diverges, does not exist. but we can't say it's equal to positive infinity or negative infinity because they both don't go to the same spot, right? Up here they both went towards positive infinity, so we said it diverged towards positive infinity. Here one goes towards positive infinity and the other goes towards negative infinity, so we don't say it exists either one of those, we just say it doesn't exist, period. Okay, so that's another way it might not exist. The other thing that we could talk about is, let's look at this graph. I've got f of x equals, we'll write it as a piecewise function, say the sine of 1 over x if x is not equal to 0, and it's equal to 0 if x equals 0. So let's look at the graph of this thing. Okay. So this is the sine function, and the sine function oscillates between positive 1 and negative 1, right? And it oscillates as you put in numbers that get bigger and bigger, right? The sine looks like this. Starts at 0, and as I go off towards infinity, it just keeps oscillating. So if I put in smaller and smaller x values, the thing that I'm putting into the sine function is getting bigger and bigger and bigger, right? So as x gets bigger, this thing is going to oscillate faster and faster. So I've got this, and it's going to just start going really, really fast in here. It's pretty much just going straight up and down as I get towards that. And the same thing from this side. It's going to oscillate, and then all of a sudden it's going to start getting really, really fast up and down. And then there's going to be a point right here at the middle because I've got 0, 0 on this graph. Okay. So I've got this point at 0, 0 from this. And then I've got the sine function when I'm not equal to 0. Okay. If I was trying to follow around a point on this curve as we were getting closer and closer to 0, it would just start jumping up and down all over the place, right? And it's going up and down so fast, it's not actually approaching anything, right? And remember, we don't look at what's happening specifically at the point. We don't look at this. We want to know what's happening around the point where I would be taking the limit. So this limit, as x goes to 0, of this f of x does not exist because all of this oscillation's happening and there's no one specific output that things are getting close to. All of these outputs could be anywhere between -1 and +1. So the limit does not exist because this oscillation's happening. Okay. So those are the three graphical ways that limits might not exist. Okay. Let's look at some graphical ways where we can kind of find limits. So let's look at a piecewise graph, and we're going to find a couple limits on this piecewise graph. So I'm going to have this point here, solid. We'll go up. We'll have a circle. We'll have a hole in the graph there. We'll put a solid dot up here. We'll have a solid dot there. We'll go off this way. And we'll go off this way. And head off that way. Head off that way. Okay. So we've got this piecewise function. Let's maybe call that at 1, and that at 2, and that at 3. And this is maybe at -2. Let's call this at 1, and this at 2, and this value up here is at 3. And this value is at -1. Okay. So I've kind of got all of these important points labeled. Let's find some of these limits. Let's see. What is the limit? We'll call this graph f of x. What is the limit of f of x as x gets close to 0? Well, as my x values get close to 0 here and here, I'm approaching this point right there. There's no jumps, there's no anything weird happening there. It's all connected, the graph is connected. So this is f of 0, which is 0 in this case. There was no jumping around or anything, no discontinuities. Okay, let's look at another one. Let's look at the limit of f of x as x approaches 1. So as I get close to 1, I'm getting close to that value, and I'm getting close to that value. Remember, we don't look at this point. Don't look at this. We don't look at the point that's on the graph, but we look around the values of 1 and see what's happening as I get close to them, right? If this function was nice and smooth and everything, the limit is the value the function would want to be. And it looks like we would want to fill in that hole for this limit. So this limit is going to be what that output would be if we could fill in the hole, which is 1, right? This 1 value is what the output would want to be if we could fill in that hole. So that's what that limit is. Let's look at, say, the limit as x approaches 3 of f of x. So we're going to focus in on 3 now. As I get close to 3, what does the graph do? The graph goes this way. If I'm coming in from the left, it looks like the function value wants to be a 2. It's 2's all along here. So as I get close to 3 from the left, I would want to be at a 2. As I get close to 3 from the right, it looks like it wants to be 3. So from the right, the function wants to be 3. From the left, the function wants to be 2. Because 3 does not equal 2, this does not exist. There's a jump discontinuity there. Okay, so graphically, that's what's going on with these limits. Let's do one really quick numerically, and then in the next video we'll talk about how to compute these things algebraically. So let's look at a function. Let's look at f of x equals, say, x squared minus 4 over x minus 2, and we want to look at the limit as x goes to 2 of f of x. Okay. This is a rational function, so you might think it's continuous, and if it was continuous we could just plug in this 2 value and see what happens, but if I plug in this 2 value, I get 0 divided by 0. And if you get 0 divided by 0 in one of these expressions, there's a good chance you'll be able to do some algebraic manipulation and maybe cancel something out or whatnot and see what happens. But since we can't plug in 2, I get division by 0, we're going to plug in numbers that are really, really close to 2. And if you plug into your calculator numbers that are really close to 2, let's say I take x and then I've got f of x out. Let's say I plug in 2.1. If we plug in 2.1 into the calculator, I get 4.1 out. If I plug in 2.01, I get 4.01 out. If I plug in 2.0001, I get 4.0001. So it looks like as I'm getting closer and closer to 2 from above, my values are getting closer and closer to 4. So 4 is probably a good candidate for this limit numerically. Let's see if that happens when I plug in numbers from below. So into the calculator we plug in 1.9, and what do we get out? We get 3.9 out. We plug in 1.99, so I'm getting closer to 2. It happens that I get 3.99 out. I plug in 1.9999, I get 3.9999 out. Okay, so again, as my numbers are getting closer to 2, my outputs are getting closer to 4. So numerically, there is strong evidence that this is equal to 4. We haven't actually proven anything, but numerically, it really does look like it's going to be 4. So numerically we can kind of do this and get a good approximation. Graphically we can do it and get a good approximation. And then in the next video we're going to see how we actually do this with the math and prove that limits equal something using this algebra.